Okay, welcome everyone to CECS 228. This is week 9 lecture video number 2, and we're going to be picking up on example 24 of basic structures part 2, which deals with functions. Now example 24 we did cover in part during last lecture's video, so I am going to go over what it is that we were able to accomplish at that time. The ultimate goal is to prove that the floor of 2x will be the same as the floor of x plus the floor of x plus a half. And so what we notice is that if we let x be represented by the sum of an integer and some epsilon part, then 2x would be 2n plus 2 epsilon, which results in a floor of 2x being two different possible answers. If epsilon is between 0 and a half, then the floor of 2x will be 2n. And if epsilon is between 1/2 and 1, then the floor of 2x will be 2n plus 1. So we were able to prove that in the case where epsilon is between 0 and a half, that the floor of 2x, which is 2n at that point, will indeed equal the floor of x plus the floor of x plus a half, because both of those gave us n each, and so if we take the sum of the two, we'll get a 2n. So now what we're going to be proving is that the equality of the statement still holds even when epsilon is between 1/2 and 1. So this we'll call case number 2. Okay, so again, we should take a look at what is the floor of x. Well, the floor of x is going to be the floor of n plus epsilon, because that is what x is represented by, an integer plus some epsilon part, some decimal part. And if we take a look at where that lies on the number line, this would be n, this would be n plus 1/2, and this would be n plus 1. N plus epsilon, epsilon lies between 1/2 and 1, so that means that n plus epsilon has to be somewhere in this range. And because it is somewhere in that range, the largest lower bound, that is an integer lower bound of any number found in this range would be n. Right, so in this case, this is n. Now if we take a look at the floor of x plus a half, that's going to be the floor of n plus epsilon plus 1/2. And what does that mean? Well, again, if we do a little bit of side work, epsilon is between 1/2 and 1. So then if I add a 1/2 to all three parts of the inequality, we're going to get that epsilon plus a half is greater than or equal to 1 and less than 1.5. So therefore, if we add an n to all three parts of this inequality, we're going to get that n plus 1 is less than or equal to n plus epsilon plus 1/2, which is less than n plus 1.5. So between what two numbers does this n plus epsilon live, n plus epsilon plus a half live? Well, it lives between n plus 1 and technically n plus 2 if we're considering only integers. So that means that the floor of this quantity is going to be n plus 1. Okay, so now comes the verification of the equality. Is it true that the floor of 2x is the same as the floor of x plus the floor of x plus 1/2? Well, if we take this and replace by n and n plus 1, we're going to get that the floor of x plus the floor of x plus 1/2 is simply n plus n plus 1, and that'll give us a 2n plus 1. And the floor of 2x, we found earlier, we said the floor of 2x will be 2n plus 1 if epsilon is between 1/2 and 1, which is the case that we're currently considering. So that means that this is a 2n plus 1. And so we see that both of these quantities agree, so the answer to this is yes. And now we've proved it. We proved the statement entirely because the only values that epsilon could ever attain is either 0 or any decimal that is less than 1. And so in those cases, for those values, we consider the two different cases of the floor of 2x, and we've already proved those cases. So then this is completely proven. All right, example number 25. They're asking us to prove or disprove that the ceiling of x plus y is equal to the ceiling of x plus the ceiling of y, where x and y are any two real numbers. So they don't specify whether this statement is true or false. I would say whenever you have this type of problem, always try to first look for a counterexample that could disprove that this is always an equality or that it holds for all real numbers. And then if you cannot think of a counterexample, then proceed to trying to prove rigorously, just like what we did in example 24. And so let's try to think about counterexamples. What I first would like to test for something like this is maybe two numbers, two non-integers that have decimal parts that are less than half. Because when we take the sum of those two numbers, they're still going to be below a minimum integer. So here's what I mean by that. Let's suppose that we choose x is equal to 1.3 and y is equal to, say, I don't know, let's say like 2.1. When we take the sum of these, the decimal parts are not going to go on to the next integer. They're going to stay at something that is less than 1.0. So if we take the sum, we're going to have a 3.4. That means that the ceiling of x plus y will be the ceiling of 3.4, which is 4. And then if we take the ceiling of x plus the ceiling of y, well, that's going to be ceiling of 1.3 plus ceiling of 2.1, and that'll be a 2 plus a 3, which is equal to a 5. And so here we can see that they're not equal to each other, so therefore this is not a statement that holds for every real number. Okay, so that is our our counterexample. All right, we're now going to take a look at the factorial function. We're going to let n be a natural number, and so that means that it could be 0, 1, or any other positive integer. The factorial function is defined from the set of natural numbers to the set of positive numbers, and it is defined to be the product of n times n minus 1 times n minus 2, all the way down to times 2 times 1. And so in short, that's written just with this, what seems like an exclamation mark. At 0, that's where we have to be careful though, because if you notice, this is the product, the smallest factor of this product is a 1. So if you take 0 factorial, that is not actually 0. That's just defined to be 1. Okay, so in general, we have 0 factorial, and actually let me correct that. 0 factorial is 1 always. Alright, so let's take a look at what are the values of f of a is equal to a factorial for the given values of a. So for 3, we're going to have 3 factorial, which is a 3 times a 2 times a 1, and that would be a 6. For part B, they want us to find what is f of 6, which would be a 6 factorial. And we can do this by hand. This is a 6 times 5 times 4 times 3 times 2 times 1. But just so that you know, most calculators have a functionality for factorial. So for instance, if you have a graphing calculator similar to mine, you can navigate to the catalog and just search for the appropriate symbol, which would be the exclamation mark. And so there it's, I didn't type in anything before it, so it's thinking that it wants me to do, or that I want it to do factorial of my last answer. But I can just go ahead and replace that with 6, and that'll give me a 720. And then for part C, we have to calculate f of 20, which is 20 factorial. Again, in this case, I'm just going to repeat the operation, but I'm going to replace 6 with 20, and that's actually a very large number. We've got 2.43 times 10 to the 18. So I'll just write, this is actually very large. It's approximately 2.4329 times 10 to the 18. Alright, and one last definition in this set of lecture notes is that of a partial function and domain of definition. So we're going to let a tilde, and b be sets such that a tilde is a subset of a. We say that a partial fraction that maps from a to b is a function defining an assignment of a unique element in b to every element in a tilde only. That is, f is only defined over the elements in a tilde and undefined everywhere else in the domain of a. And then a tilde would be called the domain of definition. So essentially, just to illustrate it with the diagram, you have set A, and then a tilde is some subset of that set A. And then you have a set B, which is your codomain. So f is actually defined over a tilde as domain. Okay, so we have something like that. As an example, you can consider the function defined from the set of integers to the set of real numbers that consists of f of n is equal to the square root of n. And that would be a partial function where the domain of definition is a set of non-negative integers. So in this case, the domain would be non-negative integers, meaning we would define it's the set of all integers such that they are greater than or equal to 0. Or in other words, the natural numbers. And so defining it in that way does give us a function because every element that is part of this set can be placed into the square root without having an undefined value, right? If we just consider all of the integers, then we would have the negatives to plug into f, and that would result in something that is a non-real answer. So that wouldn't be an acceptable answer, and so therefore we restrict the domain over which we take possible inputs. We're now going to move on to basic structures part 3, sequences, summations, and recurrence relations. And the way that I want to introduce this is by thinking about the merge sort algorithm, which we've talked about a couple of weeks back. If you recall, the merge sort algorithm sorts an array by dividing it in half and then recursively sorting the first half, recursively sorting the second half, and then merging the results. And so if we want to analyze how many visits that algorithm performs in order to sort an array, we can think about defining a function, maybe t of n, and t of n is describing the number of visits for sorting an array size n using merge sort. Then in that case, we can describe the number of visits by saying, well, it's going to be 2 times the number of times that you need to visit an array half the size, because you are sorting the first half and then you're sorting the second half. So that would be 2 times t of n over 2. And then in order to merge them together, well, you need to compare the elements on both arrays and fill up one final array of size n that will be the final sorted array. So that is where this is coming from. This is from the merging step, and this is from the sorting the first and second halves. Okay, now the way it's written, it seems to be, defined in terms of itself, right? We don't have an explicit formula in terms of n. Rather, we have t of n depending on t of n over 2. And so in this section, we're going to be describing the tools that we can use in order to have an explicit formula in terms of just n. So we're going to start with just the definition of sequence. A sequence is a function from a set of integers to some set s. And we use the notation a sub n to denote the image of the integer n. So you can think of it as n being the input and then a sub n being the output. Okay, or in other words, you can think of a sub n as being just a function that takes n as an input, performs some type of operation, and then returns some element. So example 1, we have a sequence, and by the way, this is the way that a sequence is denoted. We have the curly braces to denote there is going to be a set that will be generated by a sub n, and a sub n is defined as 1 over n, where n is allowed to range between 1, 2, and out to any positive integer. So explicitly, what that means is that we're going to have the set of elements. When n is 1, we'll have a 1 over 1, which is 1. When n is 2, we'll have a 1 over 2, so that's 1/2, followed by 1/3, 1/4, and this is just going to continue on forever. For example number 2, they want us to find out what are the terms a1, a3, and a8 of the sequence a sub n. If a sub n is one of these given rules. So for part A, the rule is that a sub n is 2 to the n minus 1. That means that a sub 1 is going to be 2 to the 1 minus 1, which is 2 to the 0, which is just 1. A sub 3 is going to be 2 to the 3 minus 1, which is 2 squared, and that gives us 4. And finally, a sub 8, that's 2 to the 8 minus 1, which is 2 to the 7th. And a 2 to the 7th is going to give us a 128. Okay, so that's for part A. For part B, a sub n doesn't even depend on n, right? A sub n is just this constant 7. So regardless of what we plug in, we're still going to have 7. So a sub 1 will be 7, same as a sub 3, same as a sub 8. And finally, for part C, a sub 1 is going to be a 1 plus a negative 1 to the 1. So that would be a 1 plus a negative 1, which is just 0. A sub 3 is going to be 1 plus negative 1 to the third. So we're going to have a 1 plus negative 1 again, because negative 1 to the third is negative 1. So we're going to get 0. And finally, a sub 8 will be a 1 plus negative 1 to the 8, which is simply going to give us a 1 for negative 1 to the 8. So 1 plus 1 is 2. Right, so in general, this last one, if the subscript is an odd number, then we're going to have a sum that is 0. And if the subscript is an even number, we're going to get a result that is 2, right? Because we're just going to get a 1 plus 1, which is 2. On page 2, we start looking at some special types of sequences. The first one being geometric sequence. So a geometric sequence, which is also called a geometric progression, is a sequence of the form a constant, then constant times some r, and then constant times some r squared, constant times some r cubed, and the pattern continues. So we can think of these as being a constant times powers of r. In general, we would say something like an is equal to constant times r to the n, and it would be defined for n being 0, 1, and any other positive integer. So for example 3, they want us to find what is the geometric sequence with the constant being 1 and r being negative 1 and n is starting at 0. So we have the sequence defined by a 1. I'm not really going to write the constant because it's not doing much. 1 times anything is just whatever the anything else is. So negative 1 raised to the n. Here's another bit of notation that I'm going to introduce. Sometimes we write the starting index at the bottom as a subscript of the set. So we can say starting at n being 0 and going out to infinity. Other times when it's left without any of the subscript or superscript, it's just understood to start at 0 and to end at negative. And never end. Continue for positive infinity. So let's see, what is this going to result in? Well, this is going to result in a 1 when n is 0 and a negative 1 when n is 1. And then when n is 2, we're going to have a 1 again, and then a negative 1. So really, we have the sequence of numbers that just alternates between 1 and negative 1. If you want to write it as a set without any repetitions, then that would be simply 1 and negative 1. It's talking strictly about the elements. But in terms of a sequence, we care about kind of like the pattern or the order that we're seeing. So we usually list out the numbers, even if we do have repeats. Okay, part B, what is the geometric sequence with C being 2 and R being 3? Well, again, I'll just write down the rule first. That means that we have a 2 times a 3 to the n, starting at n is 0, going out to positive infinity. So that means that we'll have, when n is 0, we'll have just a 2 times a 1, which is a 2. When n is 1, we'll have a 2 times a 3, which is a 6. When n is 2, we're going to have a 2 times a 9, which is 18. We'll do one more. When n is 3, we're going to have a 27 times a 2, which is a 54. and then that pattern simply continues. The next type of sequence that we're going to consider is an arithmetic sequence. By the way, any sequence can also be called the progression. So that is a sequence of the form a constant plus d, a constant plus 2 times d, a constant plus 3 plus d. In general, we would just write a sub n is equal to a constant plus n times d, where n can range 0, 1, 2, or anything greater. So for 4a, we're looking at the arithmetic sequence that is defined by c being -1 and d being 4. So in general, we have -1 plus a 4n, where n is starting at 0 and going out to positive infinity. So when n is 0, we get a -1. When n is 1, we get a 3. When n is 2, we get a 7. And then the pattern simply continues, adding 4 each time. So you can think of C as being your starting point, and then D is just one multiple, or I should say N is a multiple of D. Okay, so we just keep adding D depending on which multiple we're considering. For part B, they want us to find the arithmetic sequence that is defined by C being 7 and D being -3. So in general, we're going to have a 7 minus 3n. N ranges 0 to positive infinity. So we start at 7, and then when n is 1, that means we're subtracting 3. And then subtract 3 and we get 1. Subtract 3 and we get -2. And the pattern simply continues. Okay, so another type of problem that they're going to ask us to do is to find the formula of a sequence. So they'll give us a list of terms, and then from there we have to determine what is the general expression for a term that is part of the sequence. So in order to do that, here are some tips that can be useful. You can ask yourself, are there any repeated terms of the same value? If so, maybe that means that you're using a -1 to the n times some value, or maybe you just have a constant. You can also ask yourselves, can you obtain a term by combining the previous terms in some way? So maybe you have to add the previous 2 terms or subtract the previous 2 terms, in which case we would have some type of a recursive definition. Or the other thing is you can also potentially have an arithmetic sequence. Are there cycles amongst the terms? So maybe if you notice that one term is negative and the next one is positive and it keeps alternating between the two, again, that could potentially be like a -1 raised to the n. Do the terms match those of a well-known sequence? And so for that, here are some of the well-known sequences. Like if you have n squared, then you'll have a 1, 4, 9, 16, so on and so forth. If you get numbers that are very close to these, it's possible that maybe you have like n squared plus a constant, or maybe a coefficient times n squared. Can you obtain a term from the previous term by adding an amount or by multiplying an amount? Okay, again, if you're adding an amount, that would be an arithmetic sequence. If you're multiplying an amount, that could potentially be a geometric sequence, or also maybe an arithmetic sequence. So let's try example number 5. We need to find formulae for the sequences with the following first 5 terms. For part A, we have 1, 1/2, 1/4, 1/8, 1/16. And so the pattern that we're probably picking up here is that there are powers of 2 involved, right? We have a 2 to the 1, a 2 squared, a 2 cubed, a 2 to the 4th. So we can take a guess and say, well, it seems like this is 1 over 2 to the n, where n begins at 0 and continues on to infinity. And then we can test our hypothesis simply by plugging in these values and making sure that they agree. So when n is 0, we'll get a 1 over 2 to the 0, which is a 1 over 1, which is 1, so that looks good. When n is 1, we get a 1 over 2 to the 1, which is a 1/2. When n is 2, we get a 1 squared, a 1 over 2 squared, which is a 1 over 4. And so we see that that is going to work well with what we were given. So that is going to be our final answer. Okay, for part B, we have 15, 8, 1, -6, -13. If you notice, it seems like we are decreasing by a constant amount in order to get to the next term. So like if I do 15 minus 7, I get 8. If I take 8 minus 7, I get 1, so on and so forth. So then what the formula that seems to fit here is, or the type of sequence that seems to fit here is an arithmetic sequence. We're starting at 15, so we could write it's going to be 15 minus some multiple of 7. So starting with n being 0, 1, 2, and any integer greater than that. So when n is 0, we get a 15 minus a 0, which is 15. When n is 1, we get a 15 minus a 7, which is an 8. When n is 2, we get a 15 minus 14, which is 1. When n is 3, we're going to get a 15 minus a 21, which is a -6. And the pattern just continues. So we write our final answer in the form. It's the sequence defined by 15 minus 7n, where n is 0, going out to infinity. Right, so for part C, we have the sequence 1, 7, 25, 79, 241. This one's a little bit more complicated in that we don't have a constant difference between the numbers in the sequence, and we don't have explicitly a power of, say, like 2 or 3. So the next best thing to do is check to see if maybe there is an approximate factor difference between two subsequent elements. So what I mean by that is notice the following. If I take, for instance, by the way, I've listed the index numbers or the input. So for n being 2, if I take the ratio of A2 to A1, we're going to have a 25 to 7, which is going to be approximately 3, because 25 divided by 7 is going to give us like 3 point something. If I take the ratio of A3 to A2, that's going to be 79 to 25. Again, this is very close to 3, because if this were a 75, then we would have exactly 3. So we actually see a difference of 4, right? If I take 79 divided by 25, I'll have 3 remainder 4. And notice that's starting to look like a pattern, because here if you take 25 divided by 7, we'll get 3 remainder 4 as well. Let's see what happens when we take A4 divided by A3. We're going to get a 241 divided by a 79, which is also going to be approximately 3, because if this were 240 and this were 80, 240 divided by 80 is 3. In fact, let's go ahead and see what is 79 times 3. That's going to give us a 237, which is again a difference of 4 between 241 and 237. So we can, because we are seeing this pattern, we can make the next observation. If I take a look at A1, which is 7, that is 1 times 3 plus 4, right? Or in other words, it's going to be, and this is actually A0, right? These numbers, that is actually A0. So it's A0 times 3 plus 4. If I take a look at A2, which is 25, that's the product of 7 times 3 plus 4, where 7 is A1. Is that first, the term A1. If I take a look at A3, which is 79, that's the product of 25 times 3 plus 4, and 25 is A2. And finally, if I take a look at A4, which is the 241, that's the product of 79 times 3 plus 4. That means that it's A3 times 3 plus 4. So in general, then, what we're seeing as a pattern is that we have a sequence. Well, let me actually just first define AN. We have a sequence in which AN is defined as 3 times the previous term, so that means 3 times A sub n minus 1 plus the constant 4. Okay, so plus 4. And so we end up with the sequence defined in that manner. 3 times A sub n minus 1 plus 4 for n being, well, here's where we have to be careful. This is for n being 1, 2, 3, 4, and anything greater, right? We can't start it at 0 because then a at 0 would depend on a sub 0 minus 1, which is a negative 1, and no such element exists, right? So we have to start it at 1 and go all the way up to infinity, and then make note that a 0 is actually 1. Alright. And one last one. Here we have 2, 3, 5, 8, 12, 17. Initially, it might seem like we're adding the previous two numbers to get the next number, right? 2 plus 3 is 5, then 3 plus 5 is 8. But then that pattern breaks because we have 5 plus 8 is not 12, it's actually 13. So that is not what we're looking for. That means that we're going to continue to consider other possibilities. If we take a look at maybe multiplying certain things between the numbers, that also doesn't work, right? 2 is actually right next to 3, so there's nothing times 2 that would give us something close to 3. I mean, we could do like 2 times 2 minus 1, and then say 3 times 2 minus 1, and that seems to be okay because 3 times 2 is 6, minus 1 gives us 5. But then the moment that we do 5 times 2 minus 1, that would actually give us a 9 instead of an 8. Right, so that's not it either. And so at that point, maybe it's a good idea to go and look at our list of common sequences. We have n squared with elements 1, 4, 9, 16, 25, 36. Does that look anything like what we have? Not really. Okay, in fact, does it look like it falls under any of these? Well, not exactly. I mean, in part D, we have 2, 3, 5, 8, 12, 17. If you look, there really is no difference of a factor between any two terms, any two subsequent terms. So what we have to do now, or the next most natural thing to maybe consider, is to look at the difference between the two terms. So the difference between 2 and 3 is 1. The difference between 3 and 5 is 2. The difference between 5 and 8 is 3, between 8 and 12 is 4, between 12 and 17 is 5. So it seems like we are adding one integer greater every time. And just so that we can come up with the general rule, let's write our observations. Again, this is going to be n equals 0, 1, 2, 3, 4, and 5. Okay, so for A1, that is simply a 2 plus a 1, which is A0 plus 1. For A2, which is, by the way, 5, that is a 3 plus a 2, which is A1 plus 2. A3 is 8, which is a 5 plus a 3, and that is a 2 plus 3. A4 is 12, which is a 8, an 8 plus a 4, and that is a 3 plus 4. So in general, we're seeing the pattern an is a sub n minus 1 plus n, right? So it depends on the previous term plus whatever this subscript defines. So to finally write the formula for our sequence, we're going to define an is equal to an minus 1 plus n, starting with n is 1, 2, so on and so forth. And then we need to define a0 because remember, when we plug in the 1, we'll have an a0 here, which means we need to have an initial value, and that is 2. Right? They gave us a0 to be 2. Okay, so this is similar to what we saw in part C, where we had an defined in terms of a previous term beginning at n equals 1, 2, 3, so on and so forth. And then at a0, we had some initial value of 1.